Let's answer this problem. Example 2, calculation of partial molar properties. The enthalpy of a binary liquid system of species 1 and 2 at fixed temperature and pressure is represented by the equation. Okay, this is the equation where H is in joules per mole. Determine first the expressions for the partial molar properties of species 1 and 2 as a function of x1. Next, numerical values for the pure species enthalpies H1 and H2. And lastly, numerical values for the partial enthalpies at infinite dilution. So H sub 1 bar in infinity and H sub 2 bar infinity. So there should be a bar right here. Okay, we begin by writing the given in the problem. Given in the problem, we have the equation. I won't rewrite the equation anymore. So given the expression for H, or let's put it as H as a function of x1 and x2. A function of x1 and x2, right? And then we're also given the um so the assumption is fixed temperature, fixed T and P. What else? Okay, so that's about the given the problem. So required letter A, the partial properties, H2 and H1 and H2 bar. Next is numerical values for so so by the way, for letter A as a function of x1. So letter B is values for the pure species H1 and H2. And letter C is the infinite values for the infinite dilution H1 and H2. Okay? Mm, we begin the solution by okay, let's try to first derive expressions for the partial properties as a function of x1. All right. Uh, remember that x sub 2 is 1 minus x1, and then we substitute, okay, this expression 1 minus x1 to x sub 2 in the equation. Okay, so because the goal here is to get expressions of the partial properties as a function of x1, so we try to remove x2 from the equation. Alright, so here we substitute x2 for 1 minus x1. Okay, and then x1 times x2. So we substitute 1 minus, oops, that should be x1, and then 40 x1 plus 21 minus x1. Okay, so we're able to remove x2 from the equation, and simplifying everything, I will skip to the part wherein I almost simplified. So 600 x1 plus okay, so this is already the third step in simplifying the equation above. I'll let you do the other steps, intermediate steps on your own. This one cancels out, and uh the equation further simplifies to, to this one. Okay, 600 minus 180 x1 minus 20 x1 cube. Okay. Again, there's some intermediate steps. I'll let you do that. It's just algebra, so you can do it on your own. This is an important equation because we are now able to express enthalpy in terms of x1. So let's name this equation as equation A. Okay, so this is equation A. The rest of our um, the rest of our derivation will start or will involve equation A. First, let's try to take the derivative of equation A with respect to x1. Take the derivative of equation A with respect to x1. Okay, so that is dh over dx1. So the derivative of a constant is 0, right? Then 180, and then 60 x1 squared, correct? And then we go back to the partial properties that we derived previously. Let me open that slide. Okay, I forgot to press the record button. Not sure where we left. Okay. But I guess um I was showing you the following slide. Okay. All right. So showing you this slide, and then remember we derived this in our previous video. Okay, by first assuming the summability equation and then assuming T and P are constant, we're able to get the expression for partial properties as a function of composition at constant temperature and pressure. So we make use of this equation, but we replace M with H because these ones are general equations. So the property M can be any property like H or V, etc. For our purposes, we replace it by equation H here. Okay, so this is already um, that equation in terms of H. Now, uh, we have a term here, H and also dH over dx1. We can now replace H with equation A. Okay, we input that to H and dH over dx1 we replace by our derivative that we obtained. So doing that, so H is replaced by equation A and then time plus x2 multiplied by the derivative dH over dx1. So this is just the expression right here, which I replaced. Okay, so I hope that's clear so far. And then what else do we need to do? We have to remove the x2, okay, because we are deriving as a function. Our goal is to make the equation as a function of x sub 1. So we replace the x2 with 1 minus x1 again. Okay, so with that, our equation, okay, it becomes 1 minus x sub 1. So this is the x2. Okay, so I already distributed x2 with to the rest of the terms inside the parentheses. And okay, minus 60 x sub 1 squared 1 minus x1. All right. Next step is to simplify this equation. 600 minus 180 cubed minus 180 plus 180 x sub 1 minus 60 x sub 1 squared, 60 x sub 1 cubed. And there are terms that would cancel out. This one and this one. Okay, that would cancel out. Further simplifying, we have an expression for the partial molar property of species 1. X sub 1 cubed. And this is actually our answer for letter A, H sub 1. Let me put that inside a box. And let's name this as equation B. Okay? Uh, Now that we're finished with H sub 1 bar, the partial molar enthalpy of species 1, let's move on to uh, H sub 2 bar. Okay, so we use the other equation, which we derive, this one, uh, in terms of enthalpy. Okay, so we replace that, the property M, okay, we replace with enthalpy, so that is H2 bar equal to H minus X sub 1 dH over dx1. Okay, so like before, like what we did before, we replace H with equation A and dH over dx1 with the derivative. Okay, so let's do that. Uh, 600 minus 180 x sub 1 minus 20 x sub 1 cube minus x sub 1, then the derivative 180 minus 60 x sub 1 squared. Further simplifying the equation, okay, I'll skip the simplifying steps and proceed with the final equation. This is what we'll have for, okay, for the expression of the partial molar property of H sub 2. Okay, partial molar enthalpy of species 2. I mean, let's name this as equation C. Okay, and those two are our answers for letter A. Let's proceed with letter B. Okay, so now that we have expressions for the partial molar properties in terms of x sub 1, okay, the next required uh, value from us is actual values for the pure species enthalpy of species 1 and 2. Okay, so what we need to do here is to look at either equation A. So first we begin with H sub 1. H sub 1. We look at either equation A or B, right? If we're talking about pure species x sub 1, what is the mole fraction of x sub 1? It should be 1, right? Because it's purely species 1. So mole fraction should be 1. So by simply replacing x sub 1 with 1, like quantity 1, we can get the pure species enthalpy H sub 1. Okay. We can either use equation A or equation B. Okay, by simply just replacing x sub 1 with 1. So let's try first. Let's replace equation A. So that would be 600 minus 180 times 1, okay, minus 20 times 1 cube, and that would give you 400 joules per mole. This should match Okay, the answer if we use equation B. So let's replace x sub 1 with 1 in equation B. The answer is also for uh, joules per mole. So that is H sub 1. For H sub 2, uh, what should be, so what should be X sub 1 if we're talking about a pure species of 2, of species 2, right? Then X sub 1, in a binary solution, then X sub 1 in that scenario is 0, okay? Because it's purely species 1, so that means X sub 2 is 1, and X sub 1 is 0. So we simply substitute 0 to X sub 1 to get the pure species a property enthalpy H sub 2. Okay, let's do that. Let's do that, and that means 180 times 0 times 0 cubed, and this would give us 600 joules per mole. We can also use equation C, okay, and similarly just replace X sub 1 with 0. So this is also, oops, joules per mole, 600 joules per mole. Okay, so I hope that's clear. So that's our answer for letter B, the pure species. We just obtain it by setting either x sub 1 or x sub 2, 0. Right? For letter C, we're being asked for the infinite dilution partial enthalpies. Okay. What does an infinite dilution mean? Okay? If we're talking about species 1, the infinite dilution of species 1 occurs when x sub 1 is 0 or approaches 0. Okay, so it's 0. So that means we can use equation A, or equation B rather. We use equation B and set x sub 1 as 0. Okay. So we use uh, equation A, okay? We use equation A and set x sub 1 as 0, we would get 420 joules per mole. Okay. For H sub 2, we simply use equation C, so for H sub 2, but um, what should be X sub 1, right? So if we're talking about the infinite dilution of species 2, so that means x2 is 0. What should be x sub 1? X sub 1 should be 1, okay? Because the infinite dilution happens to species 2, so we simply set uh, x sub 1 as 1, okay? 600, so that would give us, so again, uh, let me write it here. So it's clear set x sub 1 as 0. Uh, use equation A and set for here use, oops, not equation A, but rather equation B. here use equation C and set x sub 1 as 1. Okay. Alright, so I hope that's clear. When we're talking about infinite dilution for species 1, that means x sub 1 is 0. For the infinite dilution of species 2, that means x sub 1 is 1. Okay, so this ends the solution for example 2. Okay, now that we are done solving example 2, which is on the calculation of partial molar properties, let's try to answer the next problem, which is on the graphical determination of the partial molar properties. We are given a binary mixture of 10 mole percent chloroform, which is species 1, and acetone, species 2, okay, at 333 Kelvin and 10 bars. Given the experimental data, this is the experimental data. It's a plot of the molar volume with respect to x2. Okay, so on the x-axis, let me zoom in. On the x-axis, we have x2, and on the y-axis, we have the molar volume. So we're being asked of first the partial molar volumes of the species at the given concentration, 10% of chloroform, which is x1. So x1 is 10%. And letter B, pure species molar volumes. Letter C, partial molar volumes at infinite dilution. So this is just like letter B and C are just like the given or the required values in example 2 or the previous example. All right, let's begin by writing the given. Okay, so we're given a binary mixture of chloroform, which is species 1, and acetone, which is species 2, where chloroform is 10 mole percent. 10 mole percent. Okay? And then the temperature, well, not really important uh, at this point because we're already given the experimental data on this temperature and pressure, but let's write that. Okay, so what else? Okay, that's about the given values in the problem. We're also given this graph. What is required from us are the following. Letter A is the partial molar properties at the given at x1 equal to 10%, okay? Chloroform 10%. And then the pure species molar volume, okay? All right. And then the partial molar properties at infinite dilution. So we begin with uh, this letter A, part in letter A. We go back to our derived equation. Let me show you the derived equation. Okay, so remember our equations for partial properties in binary solution. These two equations, again, an expression of the partial properties in terms of composition, okay, at constant T and P. Okay. So let me, since these are the generic equation, let me write that when the property is volume, okay, let's transform that when the property is volume. And specifically, I choose V sub 1. Okay, let me share that V sub 1 plus x2 dm over dx1. Okay?